Hello, this is chapter 10 from your book, Inquiry into Physics. This is chapter 10 summary. Chapter 10 is entitled Atomic Physics, and the topics we'll be covering are quantum hypothesis, black body radiation, the photoelectric effect, atomic spectra, the Bohr model of the atom, ionization energy, quantum mechanics, atomic structure, X-ray spectra, and lasers. Let's begin. All right, in the first section 10.1, quantum hypothesis. Section 10.1. States that in the first file, we take a historical approach to the three of these problems. We describe how investigations into them led to a reinterpretation of the very nature of light and the way it interacts with matter. Okay, so the phenomenon we're going to be discussing are one, black body radiation. The photoelectric effect. And finally, atomic spectra. Right, I'm going to be quoting the book a lot on this chapter because they just express it so eloquently. But here we go. Let's talk about black body radiation. Everything around you, including yourself, is constantly emitting electromagnetic radiation. At normal temperatures, room temperatures, most radiation is emitted in the infrared spectrum, in the infrared bandwidth. So very hot bodies that are glowing in the sun and emit visible light and UV radiation. So if you got to be really hot to emit visible light. The reason why you can see things is because they are actually reflecting the light. But light bulbs in the sun, and I think we touched on this last chapter, are so hot that they glow visible light. So it was determined that a perfect black body would be one that would absorb all light and other electromagnetic radiation incident upon it, and that it would also emit that electromagnetic radiation. So that's how it got its name, black body. And the electromagnetic radiation emitted is called black body radiation. Your book expresses it BBR. Right, so black body radiation. All right, and this is a typical black body radiation curve. So on the y-axis we have the intensity, so the amount, if you will, and on the x-axis we have the wavelength, and that goes from 0 to lambda is very, very large, very, very large. And we have two curves right here. This guy right here is the temperature is 5,000 Kelvin, whereas this guy, which is very hot, and this guy is still very hot, but not quite as hot. And you can see the 5,000 Kelvin curve peaks out in the visible bandwidth. And so it actually glows visible light. It is so hot that it glows visible light. Now, this guy is very hot as well, but slightly cooler, and it doesn't glow visible light. Its peak, well, a little bit, right? But its peak is in the slightly larger than visible light. I don't know the maximum wavelength in particular, but you can see that it peaks out here, and its temperature is 3,000 Kelvin. So go ahead and check out this book, or figure 10.1. In your book, it's a much better drawing than mine is, but you can see the difference between the hotter object and its black body radiation, or the radiation that it emits, versus the cooler object. And it's a very good graph. So please go ahead and look at it and study it. And try to wrap your mind around it. All right, and now I'm going to quote your book or paraphrase your book, and it asks us, why does a black body emit different amounts of electromagnetic radiation at different wavelengths? And we use the principles of electromagnetism. We can easily see why electromagnetic waves are emitted. Atoms and molecules are continually oscillating, and they contain charged particles, electrons and protons. So this system does produce electromagnetic waves. But the exact mechanism was still a mystery at this point. This was the turn of the 20th century. So there's still a lot to be discovered at this point, and actually is still many things to be discovered now. And one of the first steps on the path to solving this mystery, one of the first influential figures was a man named Max Planck. He was born in 1858 and died in 1947. He proposed that an oscillating atom in a black body can only have certain fixed values of energy. It can have a zero energy or a particular energy, 2, 3, 4, 5, and so on. So E times some kind of integer, some integer value, 2, 3, 4, 5, etc. Either 1, 2, 3, 4, 5. And this is the energy of the atomic oscillator is quantized. It has a certain quantity that you can't break it down smaller. In other words, if I took a piece of paper and I were to fold it in half so many times, there would come a point, Max Planck, if the atom were a piece of paper, that I could not half that paper anymore. That would be the minimum allowed energy. So that would be the quantized value. So the allowed energy is 0, 1 E, or 2, 3, 4, 5, ... etc. But this is the main event here. This is the minimum allowed energy, besides 0. But after that, the minimum value that the atom could oscillate at. Okay, now it bears mentioning that this was a revolutionary idea. And in addition to coming up with this idea, Max Planck also determined that the basic quantum of energy was proportional to the frequency of the oscillator. In other words, to the speed that the oscillator, well, actually the amount of times the oscillator was vibrating per unit time. And the formula would be E equals HF, where the energy, this is the energy, H is Planck's constant. And that H is going to be equal to 6.63 times 10 to the negative 34th joules times seconds, and this is the frequency. It has units of hertz. And we have another value of H in electron volts. Let me see if I can find that value. Yes. So this is also, H is also equal to 4.136 times 10 to the negative 15th electron volts times over hertz, or times seconds, or EV times seconds. And an electron volt is the amount of energy of an electron in a 1-volt battery. So this is a useful quantity to work with because it's, we often want to use these units because they're smaller than joules when we talk about atomic physics. The next mystery around this time was the photoelectric effect. And it turned out that the concept of quantization was the key to solving this as well. So, to quote your book, it was accidentally discovered by Heinrich Hertz during his experiments with electromagnetic waves. Hertz was producing E&M wave pulses by generating a spark between two conductors. The electromagnetic wave would travel in all directions and induce a spark between two metal knobs that were used to detect the wave. He noticed that when he used these knobs were illuminated with UV light, the sparks were much stronger. So somehow this UV light was increasing the current in the sparks. So this is an example of the photoelectric effect. Now this photoelectric effect was observed when certain frequencies, high frequency visible light, like X-rays, UV light, were illuminated some metals. All right, so it was known that somehow these E&M waves gave the electrons in the metal the energy to be ejected from the apparatus. So it was these free electrons that enhanced the spark of Hertz's apparatus. But a couple things about it puzzled people, and so according to your book, you would think that the brighter light would cause the electrons to gain more energy and be ejected from the surface with higher speeds. But it was found that brighter light just caused more electrons to be ejected, but it didn't increase the energies. So even more of a surprise was finding that the only frequency of the light, that only the frequency of the light affected the electron energies. Higher frequency light ejected electrons with higher energy. So even dim light with high frequencies would cause electrons to be ejected. So Albert Einstein is the one who explained this. And what he said was, he proposed that the light itself remained in bundles or packets and was absorbed in this form. The electrons in the metal can only absorb light energy by absorbing one of these discrete quanta of radiation. So the amount of energy in each quantum of light depends on the frequency, and in particular, it was E equals hf. Again, E equals hf. Coming back to Planck's old equation. So now we've learned in prior chapters that light is a wave. Remember Young's double slit experiment. But now this seemed to prove that light is also made up of particles, and we call these particles photons. So let's go ahead and do example 10.1. And 10.1 says, compare the energies associated with a quantum of each of the following type of E&M radiation. Red light, and its frequency is 4.3 times 10 to the 14th hertz. And blue light, whose frequency is 6.3 times 10 to the 14th hertz. And we've already learned that in our last chapter with the blue skies, that this has a smaller wavelength, and you see it's got a larger frequency, therefore it does have a smaller wavelength. And finally, we have X-rays. It's got a frequency of 5 times 10 to the 18th hertz. So it has a very much smaller wavelength. All right. So we're going to go ahead and do this. Is the energy equals HF. And we'll go ahead and do this for, let's see, all of them. So we've got 4.136 times 10 to the negative 15th EV over hertz. And if we use red light, it's 4.3 times 10 to the 14th hertz. We're going to get an energy of 1.78 EVs, 1.78 EVs. Similarly, with blue light, by the same procedure, we will get 2.61 EVs. And finally, with X-rays, we'll get 20,700 EVs. All right, so you can see the difference there. Now, finally, the third mystery was the atomic spectrum. All right. So if we put a prism to examine light produced by a white light, we'll find that we get a continuous spectrum. However, now if we have some sample of gas in a glass tube and we induce it to emit light by heating it, we don't find the same continuous spectrum. What we have is an emission line spectrum consisting of a few isolated discrete lines of color. So it's not emitting constant radiation at all wavelengths, only certain selected wavelengths. The explanation for this turned out to be another quantized theory and advancement in the theory of quantum physics, and it started with the Bohr model of the atom. Which states that the atoms form a mini type of solar system with the nucleus in the center and the electrons moving about the nucleus in well-defined and very specific orbits. The nucleus plays the role of the sun and the electrons are similar to planets. The electron orbits are quantized. That is, electrons can only be in certain orbits about a given atomic nucleus. Each allowed orbit has a particular energy associated. So the larger the orbit, the greater the energy. Electrons do not radiate energy, emit light while in these stable orbits. So here's the thing. Electrons may jump from one orbit to another. And in going from the higher orbital state to the lower, they emit energy. So the electron must gain an amount of energy to jump from that orbit, the stable orbit, to a higher energy. And it doesn't like to stay there. And when it comes back down, it emits that same amount of energy. And it does so in the form of light or photons. And that is what this atomic spectra is. So the energy of emitted photon would be delta E equals E from the higher orbital to E of the stable orbital. And we have, let's see, somewhere in the book we have a hydrogen atom, I believe, orbital values of a hydrogen atom. Here they are. It's on page, it is hydrogen, right? Yeah. Page 408. You can see the energy levels of electron orbits in the hydrogen atom. So 408 and 409. And you can calculate the actual energy differentials between these orbits, and we'll be doing that probably a little later. All right, this is section 10.5, quantum mechanics. And I'll go ahead and read you the introduction. It's good here. The success of the Bohr model of the atom, even though it was at odds with the accepted principles of the time, indicated that perhaps a new physics was needed to describe what goes on at the atomic level. So Louis Victor de Broglie, 1892 to 1987, proposed that electrons and other particles possessed wave-like properties. Einstein had shown that light had both wave-like and particle-like properties, so why not electrons? And the wave associated with any moving particle has a specific wavelength called the de Broglie wavelength. And our formula for that is lambda, that wavelength, equals h over mv, the momentum. So let's do example 10.2. 10.2 says, what is the de Broglie wavelength of an electron with speed 2 times 10 to the 6 meters per second? And that is the approximate speed of an electron in the smallest orbit of hydrogen. So we're going to find, this is V. We have to find the mass of an electron, and that's given in the back of the book, which is 9.11 times 10 to the negative 31st kgs. So we are going to have our momentum, remember our lambda equals h, Planck's constant over mv. So our momentum is going to be 9.11 times 10 to the negative 31st kg times 2 times 10 to the 6 meters per second. And we're going to get 1.995 times 10 to the negative 24th kilograms meters per second. And if we take our formula H over mv, we're going to have, I'm going to use joules, 6.63 times 10 to the negative 34th joules times seconds, divided by our momentum there, 1.995 times 10 to the negative 24th kilograms meters over second. And we're going to get a value of lambda equals 3.32 times 10 to the negative 10th meters, or 0.332 nanometers. Okay, and now once we know the wavelength, we know that the orbit has got to be the circumference, that orbital distance has got to be a multiple of the wavelength. So knowing that, we've got example 10.3 to solve, and it says, using the results in 10.2, find the radius of the smallest orbit in the hydrogen atom. Well, we know that wavelength, the smallest orbit is one wavelength. So lambda equals 2 pi r, which is the radius of a circle. So this is going to be equal to 0.332 nanometers. So we need to find r, so 0.332 nanometers divided by 2 pi is going to give us that radius, and that's going to be 0.0529 nanometers. All right, atomic structure. Okay. When determining the frequency of radiation emitted or absorbed by an atom, the important quantity is the difference between the electron's initial and final energy. Remember, it jumps up to that excited state and comes back down to its ground state. And so that difference in energy is emitted as a photon with a particular frequency reflecting that difference in energy, which we found out was E equals Planck's constant times the frequency. So now for the hydrogen atom, the lowest energy level, which is the innermost orbit in the Bohr atom, is called the ground state. Okay, the higher energy states are referred to as excited states. So now we can represent this structure using an energy level diagram, and this is on page 408 of your book. Okay, so this is the hydrogen atom energy level diagram. So each energy level is labeled with a quantum number n, beginning with the ground state, which is n1, and continuing up. All right, as the quantum number increases, the energy increases associated with that step. As n gets larger, the energy difference between the adjacent states becomes smaller. All right, so you see we've got between n1 and n2, there's a big gap. n2 and n3, there's a small gap. n3 and n4, it's even smaller, and it gets progressively smaller. Okay, finally we come to n equals infinity, if you can see that, and that is what's called the ionization energy, and that's kind of like escape velocity with Earth. So if the electron achieves this energy, it's free. Like if the rocket or whatnot achieves that escape velocity, it's free. So that is called the ionization limit. So please take a minute, study these. You've got the energy level diagram for hydrogen in your book. And finally, we will solve example 10-4. Example 10-4 says, find the frequency and wavelength of the photon emitted when a hydrogen atom goes from the N3 state to the N2 state. So N3 to N2. All right. So we first find the energy of the photon, then use that to determine its frequency. So the photon energy equals Planck's constant times the frequency equals delta E equals E3 minus E2, which is a negative 1.51 EVs minus a negative 3.4 EVs. So we're going to get 1.89 EV. Now, F equals delta E over H. So that's going to be equal to 1.89 EVs over 4.136 times 10 to the negative 15th EVs per over Hertz. And so we're going to have 4.57 times 10 to the 14th Hertz. Okay, and to summarize, we have transitions from higher energy levels to the ground state result in emission of UV photons. This series of emission lines is referred to as the Lyman series. Transitions from higher energy levels to the N2 state result in the emission of visible photons. This series of lines is referred to as the Balmer series. The transitions from higher energy levels to the N3 state result in the emission of infrared photons. This is called as this series of emission lines is referred to as the Paschen series. And downward transitions to other states result in the emissions of infrared or other low energy photons. So this is N1, N2, and N3. And this is hydrogen atoms. And this concludes our chapter summary for chapter 10.